So here we're going to do an example, total potential energy of a spring. Okay, so we're going to, in this example, we're going to determine the displacement of node 2. And our problem, we have a spring here. Node 2 would be connected to another spring in parallel with another spring. These are rigidly attached. Node 1, 2, 3, and 4. So we have our x direction and I should have probably used a different color here, but we have our force that's pretty hard to see. Let's change that to yellow. All right, so we're pulling there. Of course, we give these springs some stiffness values. That's our problem. So determine the displacement of node 2. Kind of interesting spring problem. We can write some boundary conditions down here that will help us out. So d, the displacement at node 1, d1 x is going to equal to 0. We could drop the x because we're just looking at 1d here. We also have d3x equals 0 and d4x equals 0, right? Those nodes aren't going anywhere. They help us later on. You'll see that those will help us actually simplify our problem. The next thing we can do is write down the strain energy of the problem. And if you remember, we call that big U. Okay, so big U, and we sort of go from, we can just go from left to right here. The strain energy, we're going to have 1/2 K1 strain energy of that element there, and we're sort of you tend to think of these things in terms of start to think about these things as elements. So these springs are kind of like elements with a stiffness. So 1/2 K1 for that section between 1 and 2, and that displacement 1's not going anywhere, so you're going to have d2 x squared here. And then we're going to have 1/2 K2. We'll go up to this top one between 2 and 3. And there we could take the displacement of 3 minus the displacement of 2. Right? So, of course, displacement, you know, we if in sort of hindsight, we know that, or I guess not in hindsight, but we know that D3 is going to be 0. So we can actually drop that out. But for right now, I just want to keep it in there because it demonstrates that, you know, 3 could be moving, and we'd have to subtract, we'd have to consider the movement between 2 and 3. So that's why I'm including it here now. And then finally, that last element, which is going to be 1/2, oops, make it a little neater, 1/2 K3, and that's d4x minus d2x. squared. That's our strain energy. And we can also write down now the external work done. All right, we call that W, and that's going to be equal to R minus F d2x. Force times the displacement. We give that a negative value because that's going to be pushing as the opposite way of the strain energy. So it's meant to balance that out, right? So you can think about it coming into the system is negative in this case. But we want these things to sort of equilibrate each other. Okay, so we would add those up to get the total potential energy, right? So it'd be U plus W, and that would have a negative sign with a negative F. Now, if we want to obtain equilibrium, so we could obtain equilibrium equations by minimizing the total potential energy pi with respect to unknown displacements. All right, in that case, we can write our total potential energy with respect to unknown displacements, which is just dx2, right? So we write d pi over d 2x, I guess we were calling it. Actually, we have d dx2, right, to be proper with what we've been using, convention. So then we have, if you take those derivatives, you get k1 d2x minus k2 d3x plus k2 d2x minus k3 d4x plus k3 d2x minus f. That's equal to 0. We set that equal to 0 here to minimize, right? To minimize. And you can rearrange that. Of course, this is from these, we had those square terms expanded, so that's kind of how I expanded that out, and I took the derivative. And we can rearrange one more time to get k1 plus k2 plus k3. This is nice to organize terms of the displacement. d2x minus k2 d3x minus k3 d4x is equal to f. So we look at this and we say, well, we know what these are, right? This is equal to 0. This is equal to 0. So then we can solve for our d2. So we have d2x is equal to f over k1 plus k2 plus k3. And that is the displacement of node 2. So pretty interesting. We used, now it's important here is we used those boundary conditions, those known boundary conditions to help simplify our problem. If we didn't have those or they were unknown, we would keep these in, okay, and we would have to write other equations with derivatives, right? So we would write d pi d d3x d pi d d4x, okay, and they would, you'd have those if they were unknown, and we would set those equal to 0, and that would give us a system of equations which we could then solve. In this case, we're just keeping it easy and for demonstration purposes, but we'll look at more complicated cases as we go along. So that wraps that aspect up. Let's move on now.